Good morning, good afternoon, depending on where you are in the world. Thanks for joining. We've got a great presentation for you today, diving inside the Trimble SX10 scanning total station. It's one of the most popular presentations from Trimble Dimensions, and we know you all can't make it there, so we're going to put this into a webinar and have it recorded for those that can't make it in person. This is the first Trimble Optical webinar for some time, so while I've met many of you, there's a lot I haven't. So way as introduction, I'm Derek Shanks, Product Manager for Trimble Optical, looking after the Trimble SX10 and S-Series instruments, as well as all the accessories that go along with the instrument to make up the optical system. I've been in the role here in Westminster, Colorado for 2 years now, but as you might notice from the accent, I'm not from around these parts. I was born and bred in New Zealand and spent 7 years with the Trimble Access Field Software team after finishing my surveying degree. The last 3 years of which I was the lead of the System Quality Assurance team for the SX10, so spent a lot of time getting to know the instrument very well. However, not as well as our main presenter today, who's Mikael Nordenvelt, a distinguished engineer based in Danderyd, Sweden. Danderyd being one of the main R&D sites for Trimble Optical, as well as the manufacturing facility for the Trimble SX10 and S-Series instruments. Mikael was pivotal in the design, development and production of the SX10, and you're going to hear from him shortly, but I know we're all here to get an inside look at the instrument, but I just wanted to take a couple of minutes to step back and highlight the long, strong legacy on which Trimble Optical has been built, which is the foundation that enabled us to bring the revolutionary SX10 to fruition. So I just wanted to start by showing our Trimble Optical family. We definitely have an instrument for everyone, from the C-Series mechanical through to the latest and greatest Trimble SX10 scanning total station. It is the newest, most innovative total station portfolio on the market, with everything being either brand new released or updated within the last 3 years. However, as I mentioned, the current robotics are built on an extensive, robust legacy, primarily out of two sites. The first being Jena in Germany, where there's over 100 plus years of history, and then Danderyd, Sweden, where there's over 70 plus years. So I'm just going to take a couple of minutes and show you some of the history from those two sites, which set the foundation. So starting first with Jena in Germany, which started out of Zeiss and later becoming Trimble. So Jena was the birthplace of industrially manufactured accurate surveying instruments such as levels and theodolites, initially starting with microscopes. Carl Zeiss and Ernst Abbe were two of the founders of this technology. In the early 1900s, they had the TH1 theodolite by Carl Zeiss, and the Zeiss surveying division, there was quite a lot of divisions to Zeiss, but that continued as a surveying division through until when it was acquired by Trimble, producing more instruments, as you can see down the bottom. The other side, back in Danderyd, which was Geodometer and then before becoming Trimble, had the world's first EDM in 1948. It was a Geodometer Zero. Took about 2 to 3 hours to measure and an hour to calculate the results, so we've definitely come a long way, but pretty impressive for the time. They also had the world's first total station, so in the 1970s with the Geodometer 700, the data was stored on a paper punch, so I know most of you will be glad we're not doing that anymore. Following on from that, there was the world's first robotic total station out of Geodometer, and that was in 1990 with the Geodometer 4000. And then the world's first upgradable total station in 1994, the Geodometer 600, so being able to go from a conventional autolock or robotic models and upgradable between them all. So that was a very brief history of a couple of main sites. They then combined under our Trimble Optical banner, and that's the birthplace of our S-Series platform with market-leading functionalities such as the MagDrive, SurePoint, HDR imagery, and active tracking. It was also the birth of another world's first, being the first scanning total station. We may chuckle a wee bit at the VX being called a scanning total station these days, but at the time, at 15 points per second, it was the world's first on the market in 2007. The other side with the Trimble SX10 being it's not just a high-end robotic total station, but also a high-speed laser scanner, is just to jump into our scanning history. So we've got 27 years of scanning legacy, starting out first with Menzi in Paris in France. And so in 1992, they had the first commercially available scanner with the S25. After being acquired by Trimble, they then had input into the VX, this first scanning total station, and then the birthplace of the TX series, with first release in 2013 and then updates for HDR in 2016. So with all those three sites and all that knowledge and history there is what enabled us to bring to the market the Trimble SX10. So the world's first true scanning total station, redefined what a scanning total station is, with 26,000 points per second. As I mentioned, built on that proven technology from all those sites and previous instruments, and providing high precision and the smallest spot size on the market. So that's enough from me. I just wanted to give a brief overview and show how we got to where we are today. And I'm now going to pass over to Mikael Nordenvelt to take you through inside the SX10. If you have any questions throughout, then feel free to send them in through the questions panel, and we can either answer them as we go at the end, or if we don't get to them, then we'll reach out to you afterwards. So we're also going to pop up a wee poll, just trying to get learn a bit about where you're at, and there'll be a follow-up question at the end. And so yeah, if you could answer the quick poll, it's just a yes or no multi-choice question, and while we swap over to Mikael, if you could take 30 seconds to answer that, that'd be great. So we're just swapping the presenters over. Mikael, you should get a pop-up to accept. Cool. Mikael, you may be on mute. You may just need to unmute yourself. We can see your screen now.
Okay, so sorry for that. I had some technical issues here. Now I should be ready to go. So my name is Mikael.
We can hear you.
I've been working for Trimble for 17 years now. I started here in Danderyd, Sweden, doing my thesis from the Royal Institute of Science. I started out working with the angle sensor for what was becoming the Trimble S6 that we released in 2005. And after that, I've been bouncing around all over the instruments and been working with most of our sensors. Nowadays, I'm a distinguished engineer, and I work a lot with the system side, both interaction with the marketing, trying to tell them what is possible to do, defining new projects, and participate in pre-studies. So during the Trimble SX10 development, I was initially one of the inventors, and I moved over to a system role, trying to put everything together and make sure that everything worked together. So this presentation was intended for the dimensions, as Derek mentioned. So we had it first time 2 years ago, and now last dimensions again, slightly updated, and I think this is an even more updated version. So what I'm going to talk about is start out with what is the difference between the total station and the scanner, and try to describe a little bit why it's difficult to combine both into one instrument. After that, we'll run through the angles, drives, and tilt sensor, essentially what is needed to create a high-end total station. Together with that, we need to bring something extra to allow for scanning. I'm going to go through the new EDM we had to develop to make this happen. And finally, a couple of slides on how we are producing the SX10 here in Sweden, Danderyd. So first off, what is the difference between a total station and a scanner? Starting off with a total station, as Derek mentioned, this is our background. Here in Sweden, we've been developing total stations since back in the 50s, more or less, or 60s. So a total station is about accuracy. You want to do very accurate aiming. It's used to capture discrete 3D points, and the selection of the point is done in field. So you aim at something, either by having a guy running around with a rod. You have the instrument somehow measuring a point, you transfer that to the ground, that's one discrete point. The value of this point is added by tagging it with something, telling that this was a curved line or something like that. The point itself is just a point, something was there. You can also do DR shots by measuring aiming again. So you do the selection in field, you aim, you gather a point. So we are talking about 100 to 1,000 points a day maximum, and everything is fairly slow. But you're after millimeter accuracy. On the other hand, a 3D laser scanner, now everything is about speed. So you want a fast distance meter, and you need a fast way to move that around. And now the work in field is much easier. You just say that in this general direction is where my target is. You have your EDM, and it moves as quickly as possible. You set the laser scanner to scan somewhere, and then it goes ahead and covers that area with as much point as it can in as short time as possible. Again, each point doesn't really have a value except telling you that there's something there. So now we have moved to the office to try to extract what you need. So by looking at groups of point or photographs you capture at the same time, or just trying to look at the 3D point cloud, you can try to extract, okay, what was this? And bring it into something that is useful. But the key here is that the main difference between total station and scanner is one is about accuracy, everything is slow. The other thing is still accurate, but not as accurate, but everything needs to be really fast. But there's also a similarity. Both of these instruments are about angles and distances. That's the very core of what we do with our optical instruments. And anything else we put into the instruments are really just extra systems to make these measurements of angles and distances faster, easier, more accurate. So looking at the technology to bring this to the customer, we can start with the angle sensor and drives. So these are the drives that is needed to do the high accuracy survey work. We call it MagDrive. It was developed for the S series back in 2005 and improved for the SX10. So the angle sensor is an encoder. That means that we have some type of glass disc mounted on an axis shaft that is rotating. So you can see the glass disc here. Along the edge of this glass disc, there is some type of code etched. It could be a reflective pattern or a transmissive pattern. In this case, in our angle sensor, it's a transmissive pattern. We have a light source, and we have some type of photodetector. And by looking at the interaction between this light and the code on the disc, we want to calculate our rotational position. We use two pairs of light source and photodetector, one on each side of the axis shaft. That's called diametrical reading. And the reason for that is to lower the requirements on mounting tolerances. So if you will always have some type of eccentricity when you mount the disc. So when it rotates, it's going to move a little bit, not rotate perfectly. But by reading the angle in 2 points, any translation of the disc will give an increase of the angle on one side and a decrease on the other side. So the average of these are much less sensitive to mounting errors. Another thing we introduced with this angle sensor is the use of a standard camera sensor. So back in 2005, cameras started to pop up everywhere, and they were easily available and cheap enough to work. So the good thing with this is that we have a big sensitive area with tons of pixels, so we don't have to align that to anything. We more or less just can throw it into the instrument and look at whatever we see and make it work. So again, to try to make the instrument easier to produce and more robust. So looking at the real parts in the instrument, this is the base part of the instrument that actually goes into the tribrac. You can see this upper plate is screwed to the instrument. We have the ball bearings in the center here. So this upper plate rotates along with the instrument, whereas the base and this axis shaft is stationary with the tripod. You can see the angle sensor here with its camera sensors. Then we have the angle encoder hub. So the lower glass disc here is our encoder disc with a pattern. The upper one is just a mirror to make the mounting easier. And these guys go together like this. You can see the small white dot on the circuit board. That's our LED. So the light goes up into the mirror, down through the code, and onto the camera sensor. So this is what the encoder pattern actually looks like. This is an image captured from an actual instrument. And as you can see, it contains 2 tracks. On the photograph below, you can't really see one track because the lines are so narrow, so they just look like a grayish area. But you can clearly see the other track. So one is an absolute track, and that's the lower one on the red-black image. That is used to know where on the full rotation we are, whereas the outer one is an incremental track. It's used to very, very accurately detect changes in angle. And as you can see, the use of a camera sensor makes it really easy. So we always see both tracks without problems. So how do we read this encoder pattern? Well, it turns out we haven't come to the servo drive system yet, but it's a direct drive, which means that we have to have a very high update rate on our angle sensor so we can have a tight control loop. So we have to read this really fast. So we don't really have time to read out the full sensor. A normal cheap camera sensor is built to deliver like 60 frames per second. And we want something in the order of 500 to actually 2000 in the SX10. So we only read one line of pixels in each code. And you can see here these graphs showing the intensity on the y-axis and the pixel number across the sensor on the x-axis. So starting with the incremental track, it consists of 2,808 evenly distributed lines. Each of them are about 30 microns wide. And this is red. We get 500 pixels across the sensor. And this is fed into an FPGA, and we run a Fourier phase detection algorithm on top of this. This gives us incredible accuracy. But the problem here is that we have a problem with ambiguity. So we don't know which lines we are seeing. We see like 36 lines, but we don't know where on the full time we are. So if you rotate this, one line will drop over the edge of the sensor on one side, and a new one will come in from the other side. But we don't know where we start. So that's why we have the absolute track. It consists of 2 types of lines, wide lines and narrow lines. So the wide lines are evenly distributed and divides the disk into 156 sections. In each section, we have 2 narrow lines carrying the information, and they have a unique position in each section. So by, again, having the FPGA, using a threshold value and detecting where these lines are and how much light energy is in each peak, we can calculate a rough position. And now it's time to combine this into an angle reading. So first off, we have an incremental reading, but due to this ambiguity problem, it can correspond to several different true solutions, so like 2,808 different. But if we bring in the absolute code, it will give us a reading. It's not accurate, but it's accurate enough to tell which of the solutions from the incremental track is the true one. And once we have that sorted out, we can just keep track of that solution and keep updating it with incremental changes read from the incremental code. So the absolute track is more or less only to get started and to validate that you haven't missed anything. So putting all this together gives us an angle sensor with an accuracy which is better than half an arc second. The measurement rate in the SX10 is 2000 Hertz. And just to give you some perception of the angular accuracies we talk about, 1 arc second is about one side to the other of a coin in half a mile distance. But we're not reading this at half a mile distance, we're reading it about an inch radius. And now we're talking about a couple of micrometers or less. So I think it's 0.15 micrometers 1 arc second on the encoder disk itself. But to measure accurately over long distances, the angle system isn't enough. We also need to know how the instrument is leveled. Otherwise, especially the vertical direction will be completely off. So we have a tilt sensor, also developed and inherited from the S series. It's a compact design, very durable. It only measures 6 times a second, but on the other hand, the level point of the instrument usually doesn't change that fast. Otherwise, you have other problems. So the principle is really simple. We have an LED which shines through a prism here, a lens that collimates the light so the rays are parallel. It goes into this container, which is half filled with a liquid, a silicone oil. We get a reflection from the surface that goes back to the same lens, same prism, and onto a camera sensor over here. This is what the camera sensor sees. It just more or less sees an image of the LED. But the beauty here is that the liquid surface will always be perpendicular to the vector of gravity. So if we rotate the tilt sensor, the image of the LED will move on the sensor. And by simply calculating the center of gravity on this, of the image from the camera sensor, we can very accurately calculate the level of the tilt sensor. The beauty here is that it's a simple design, it's very accurate, but on the other hand, the drawback is that we get a very limited working range. On the other hand, for accurate survey work, you still don't want to have a too unleveled instrument because other problems will arise from that. Okay, so now we have a way of measuring how the instrument is aiming very accurately. But now we also need to aim the instrument to do our survey work. And that's where the MagDrive comes in. Again, a development from the S series that has been transferred and developed further for the SX10. So like all electrical motors, it contains 2 parts. One is a magnetic system with permanent magnets, and the other one is some type of coil. And this is the magnetic system we use. It contains of this ring you see here. There are magnets sitting on each side of this air gap running along this ring. And the polarity of the magnets change from each pair so that the magnetic field goes in one direction and then the opposite direction between the next pair. There are 60 magnets in this. It's all the magnets are placed in this iron holder to couple together the magnetic fields. But to make a motor, we also need the coil, and it looks a bit peculiar. This is a 3-phase motor, so that we have 3 different wires running through the coil. You can see the 3 colors here, green, orange, and red. So the wires go up on the outside, then they go diagonal across the top and down on the inside, slightly offsetted from where they went up on the outside. This means that we will build a small coil section for each of the colors, and then it repeats itself around the full coil. Now we can combine this together with the magnetic system. You can see that this coil fits into the air gap of the magnetic system. So if you place a current in one of the coils, it will interact with the permanent magnets and sort of find its resting place where they align. And by alternating the current to these 3 phases, we can perfectly control in which direction and how much torque we are placing on this. Another interesting factor is that this coil system is self-supported. So normally when you build an electric motor, you have an iron core. That adds efficiency, especially when you're rotating quite fast. But in this case, we are trying to rotate fairly slowly. It's a total station after all. And most of all, we don't want what's called a cogging. So if you have an electric motor with an iron core, it will find its resting places in relation to the magnets. So you can feel when you turn it that it sort of gets stuck on certain position. And that's really non-ideal for a total station drive. So instead we use a copper wire that is coated with glue. We wind it and then we put it in some type of form and throw it into the oven so this glue melts. And when it comes out, it stiffens and it supports itself. And as you can see, we glue it on top of the angle sensor board so that it all goes together in a nice unit, encapsulating the encoder disk and the angle sensor. The angle sensor needs a dark environment to work in, and it also needs to be protected from the rest of the system. You can see here how the winding runs in between the magnets here. This has a lot of advantages compared to our old system, and actually what a few of the competitors still use in some instruments with the old gear system, is that we don't have any wear and tear. There's no mechanical contact between the two rotating parts. It's also silent and it's much faster, and we have much better control over this new system. So just some performance figures. It's fast. We spec it to 115 degrees per second, which means a switch phase in 2 seconds. This is actually not limited by the motor itself. It's more a limit we put on ourselves how much torque we dare to place on the setup. Because if we place the maximum torque that these drives can create, the setup would shift and destroy the accuracy. So this is limited to a switch phase in 2 seconds. But an almost more impressive figure is the other end of it. So the lowest speed we can actually control and can maintain a controlled low continuous speed is 86 microdegrees per second. And at that rate, it takes us 50 days to complete the full rotation of the instrument. So it's an incredible control we have over this drive system with the combination of this, the mag drives and the angle sensor. So now we have a way of moving the instrument to fulfill the purposes for the serving instrument, for the total station. But now we want to add scanning. So the problem with scanning, as I mentioned, is the speed. If you throw a distance meter into a total station, a really fast distance meter, what will happen is that it will measure the same thing over and over again, unless you can move it quickly enough. Or you'll end up in a situation where the only thing you can do is a really, really dense grid. So you can, for instance, scan a doorknob at 100 meters, but you can't capture a full dome scan. And on top of that, the EDM measurement spot isn't infinitely small, which means that if you don't move enough, you will start overlapping. So you measure the same thing over and over again. So when we set out to develop the SX10, we wanted to create a 1 milliradian grid. So that's 10 centimeters, that's 100 meters. We would say that we would like to capture a full dome scan in less than 30 minutes. And that was sort of a level where we thought it would be useful and somebody would actually use it. If it ends up taking 5-6 hours to capture a full dome scan, nobody's going to do that. Not in everyday work, at least. So is the MagDrive sufficient? I don't know how well this animation comes across, but MagDrive can spin really fast. As I said, we limit it based on how much torque we can place. But if we just continue accelerating, we can spin really fast. But it's still not fast enough, and it's not very practical either. Any unbalance will again shift the setup. So we looked at using the mag drives at full speed, but this 1 milliradian scan I talked about would still take more than 2 hours. And again, people wouldn't use that too often. So instead, we came up with a concept of adding a third axis of rotation. So we keep our mag drives that we need to do the accurate survey work, but then we add the third axis of rotation inside the telescope. So the idea is to have our EDM beam, but then add something that means that we can sort of slightly shift it side to side. What's the use of this then? Well, if you imagine that we aim the instrument down here, we start this deflection, moving the EDM beam side to side. We start the EDM measuring at a high rate, and then we use our slow servo drives, the mag drives, to move the instrument upwards. What happens is that we get points rolled up like this. So instead of just measuring one column of points going up, we can measure several of them. So the SX10 is actually measuring 16 columns of points simultaneously going up. And then the same thing going down. So this means that we can increase the EDM speed 16 times compared to what we could without using a deflection. So now when you want to scan something, you frame it and the instrument starts scanning by moving up and down and just quickly covering the scene with a dense point cloud. And we call this band scanning. So how do we do this inside the instrument? We looked at several different solutions using rotating mirrors and oscillating mirrors, but it turned out that in the end that the most efficient solution was a rotating polygon prism. So as you can see here, we have a laser coming in from the left, laser beam. It hits a surface that is continuously changing the angle. When it transitions from air into glass, we get a refraction. It propagates through the glass and out on the other side. And as you can see, the surface it goes out through is always parallel with the surface it goes into. So we actually get a refraction back to the original direction, but we have translated the beam from side to side. So if we remember our high school physics, any beam coming straight into a lens, parallel to the optical axis, will get refracted towards the focal point. So now we have created an angular deflection around the point over here. And there are two really big advantages of this solution compared to mirrors, for instance. So one is to get this nice band scanning with the even coverage, we really need the deflection to act like this old-fashioned typewriter. So go from one side, add points, and then immediately go back and start a new one. Doing this with an oscillating mirror means that we have to put enormous amounts of energy into that fast transition backwards, which costs energy, it's hard to control, and it causes vibrations. But we get this for free when this incoming laser beam sort of transitions from one facet to the next. So this solution inherently has that behavior. The other advantage is the accuracy. So when you have a mirror and change the angle of the mirror, the angle of the outgoing beam, the deflected beam, will change twice as much. So if you have an error in your control of that mirror, the error in the beam going out is going to be twice as big. In this solution, we get a gear ratio in the other direction. So 20 degrees rotation of the deflection prism gives us about 1 degree of deflection of the beam itself, which means that the control of this prism is much easier. So one, we can have a continuous movement of this deflection prism that is easy to maintain, doesn't cost much energy, and doesn't cause much vibration. And on top of that, we get better accuracy from it. So let's look inside the instrument and see how this was implemented. So inside the telescope, there's a lot of sensors. So through the front lens, we have the EDM with its deflection. We have the tracker sensor and the telecamera. And then we also have these two other cameras, which are non-coaxial. They are not going to be covered in this presentation. But let's tear the telescope apart. So we remove the covers. Inside, you can see that we have structure holding all the optics and electronic board, and it's completely free coupled from the side cover. So no, or at least very little influence from sunlight as such affects the optics, which makes the instrument more stable. We remove some boards, and then we rotate it slightly. Now you can see that the trunnion axis is tilted slightly upwards, and that's because we couple out light from the main optical channel in the biggest cross section of the telescope, which is not straight up and straight down, but slightly to the side. And then we slice it in two. So this is what the interior of the telescope looks like. And you can see that it's a lot of glass in there. On top, you can see the part with the EDM. So here are two fibers, one for the transmitter and one for the receiver. This is the deflection prism and its motor drive up here. And as you can see, we used the same deflection prism for both the transmitter and the receiver. So you can look at the transmitter as a laser pointer shining out to the instrument that we sort of wiggle from one side to the other. The receiver is like a binocular looking in the same direction as we shine with the laser pointer. And the reason for that is to cancel out as much ambient light as possible. We only want to look in the exact direction that we transmit the laser pulses. The transmitter goes through the deflection prism, these two lenses, and then bounces through this big beam splitter prism over here. And a beautiful thing here is that after the reflection of this back surface, we get enough angle to get total internal reflection, which means that the same surface here is actually used both for transmitting light and reflecting light. It goes back here and out through the front lens. The light goes to the target and comes back and bounces in this first surface. Again, total internal reflection and a bounce through a couple of lenses and into the receiver fiber. This surface here is where the magic happens. That's the sort of vertex point for the deflection. So both the receiver and the transmitter rotates around that point. And that surface has a coating with a hole in the center, letting the transmitter through and using the surrounding area for reflecting light to the receiver. On top of that, we have the telecamera placed down here with its focusing lens. And we have the tracker detector placed on the very back. So now that we don't have the constraint of having to have an eyepiece on the back, we decided to put the tracker in the most stable place. So all in all, we have 5 optical channels and wavelengths stretching from 450 nanometers up to 1550 nanometers. There's a lot of advanced optics in here. It's 15 optical elements in the telescope and almost a pound of glass inside. So now we have a way of moving our EDM beam. We have a way of combining that together with this total station drives and angle sensor. But now we also need this fast EDM that can still be accurate enough for the high precision total station measurements. And we started from a couple of known technologies. So we use the same principle that we use in our old trusted DR+, which is time of flight. So essentially, we flash with a laser. We start the clock when we do it. We wait for the light to transition to the target and back. We stop the clock. And that time is a measurement of the distance to the target, since we know the speed of light. But there are some differences this time. And the biggest one that I'm going to talk a little bit about is the single shot measurement. So in the DR+, a total station measurement, if you have a measurement time of 1 second, the customer is usually pretty happy. And that means that you can do a lot of averaging, adjusting, both adjusting the signal level and you can adjust timings. But in this case, we have a continuously moving EDM beam. So each shot counts. So a single laser shot needs to render a distance. Otherwise, we're going to get gaps in our point cloud. And we borrowed a few technologies from the Trimble TX8 and redesigned them to work in this context. So some of the things we have to handle to get these single shot measurements. First off, we need a really powerful laser source and with very good beam quality so that we can get a nice spot, but also a good timing property in the laser so that each laser shot has the same shape in time so that we can do averaging to get this total station accuracy we need. We also get the problem with the dynamics. So in a DR shot on 500 meters, only 1 in 1 billion transmitted photons will actually return to the instrument. Whereas when you measure to a prism, you get almost all the light back. So this distance meter has to have a huge dynamic range and it needs to transmit a lot of light to, with a single laser shot, get enough photons back to do a measurement when we're scanning. We also need to do something that is called direct sampling. And I'm going to come back to what I mean with that. Yeah, so this is the problem, that is, the photos will go all over the place. So the laser source, we had to do something different from what we've done before, both because we needed the good beam properties, we need a really small measurement beam, but we also need a lot of power. So we ended up designing a laser source of our own based on telecom components. So the principle is fairly easy. We have a seed laser, which is a nice laser. It creates a very weak but very nice pulse. So it has a good pulse shape and the sort of the frequency contents is really nice. It doesn't have much chirp, which is chirp is when you have different frequencies in the same pulse more or less, and it's going to change over time. So this creates really nice light. We let that run through a fiber here, which is doped with erbium atoms. Into the same fiber, we have a pump laser, which creates, let's call it ugly light. It's on a different wavelength, so a different color than this one. This light is continuously emitted into the fiber, and it gets absorbed by the erbium atoms. And once this nice light comes along on this different wavelength, it will interact with the erbium atoms. So it's something that was found by Einstein way back, which is called stimulated emission. So when a photon of the right wavelength interacts with the atom, it can sort of pull out the energy and create a new photon, which is perfectly aligned with the first one. So what happens is that we pour energy from the pump laser into the fiber, and when the seed pulse comes, it sort of pulls out the energy and it multiplies. So after one stage, we have gone from like 0.1 milliwatts to like 10 watts peak power. And then we have another stage bringing us up to above 1 kilowatt peak power. But a good thing here is that because of the properties of glass, and that's important for fiber communications, all these components are based on technology that creates 1550 nanometer light. And the good thing is that it is very eye safe. It actually gets absorbed in the outer part of the eye, so it doesn't penetrate much into the retina itself, and which means that we get away with more laser power in the laser class regulation. We're running this on a pulse repetition rate of 26.6 kilohertz. The pulses are about 1 nanosecond wide, and as I said, it's about 1.3 kilowatts of peak power.
Hey, Mika, we just want to jump in here. Questions come through that the whole audience is going to benefit from. I'm going to leave this one to Chris Trevelyan to answer, but how we say it measures 26,000 points a second, but often that's not going to be how many points you get per second, is the question that's come in. So we've got Chris Trevelyan here, market manager, was product manager, but I've slotted in underneath him, so he's going to take this one and answer it for everyone.
Yeah, so, and Mika jump in at any time, but a lot of times we get this question, and the ideal that, or what Mika is showing here is we have a sampling speed or pulse repetition rate of 26,000 points per second, which is the theoretical maximum raw scanning speed. You see that also with all the other manufacturers on the market. So like the high-speed laser scanners that will sample at a million points per second. But what you don't see is that that's in a theoretical environment. So if you're scanning outdoors, you don't get return off of dark material or material that's too far away, or when you're scanning the sky, all those shots are more or less wasted because you're not going to get a return. So that in effect lowers your actual sampling return, or your actual scanning speed, effective scanning speed. So that's where the difference comes between 26,000 and if you're doing a full dome scan outdoors and you're scanning the sky, you're going to quickly drop that 26,000 down to 10,000 points a second or even less, because you're wasting a lot of energy trying to scan the sky, which won't produce a return. So that shows up in every laser scanner on the market. The TX8 that scans 1 million points per second is the same. It's just the fact that when you're getting 500,000 points per second, let's say, you don't really notice the difference. You're still getting a ton of points. In this case, though, since we're only scanning 26,000 points a second, and when you come in with like 10,000 points per second, you kind of notice that difference. So that's the key here. And in a common misunderstanding, it's really hard or nearly impossible to spec an actual scanning speed because the conditions vary so widely between inside a building or outside in a urban environment or outside in a forested environment. So that's why all manufacturers will spec the raw scanning speed.
And it's also a question of how you create the deflection. If we look at the TX8, for instance, it has a continuously rotating vertical deflection, and it can't measure when it's looking down into its own alidade, and that's the same for most scanners, which means that about 60 degrees of your 360 degrees will get lost. That immediately reduces the effective scanning speed. And it's a little bit the same here. So we lose a few points when we transition from one facet to the next and when we change direction. So for all of these scanners, it's also going to depend on what frame you put up. So for a TX8, if you put a really small frame, you're going to get efficiency that is horrible, because you're still going to have this full rotation, but you're only scanning when you pass your frame. So it's inherent in the deflection principles, and as Chris says, it's also the environment and what you're scanning. So usually you're never going to get close on any scanner, get close to what the manufacturer specs, but that's sort of the run rate the EDM has to capture, because that's the highest rate it needs for some passages. So efficient will always be lower on any scanner. So looking at this again, the 26 kilohertz means that it's 38 microseconds between the pulses, and the pulses are 1 nanosecond long. It's hard to get a perspective of this, but if we scale this so that the pulse would be 1 second, the distance between two pulses is actually 10 hours. So there's a lot of no light, and not very much light. And that's also why we get away with so high peak power, because the average energy is really low. Another result of having this laser built from fiber components, if you want to transfer gigabit rates over a fiber, it's very important that all the components is something that's called single mode, which means that essentially an optical fiber is more or less like a tube which is coated with a mirror on the inside so that light can bounce through it. But when you keep going narrower and narrower, at some point physics start kicking in, and at the end you're so narrow that there's only one waveform that can propagate. So there's only one way for the light to go through. That's really important for telecommunication. For us, it's not that important, but it turns out that when the light leaves the fiber, it looks like it comes from an almost perfect point source. So we can really keep the beam narrow. We have extremely good light properties from this laser when it leaves the fiber. So that's why we can have the smallest spot size on the market. You can see here this graph showing the spot diameter on different distances. So it keeps very narrow, even for long distances. So again, going back to what I called this direct sampling receiver. In older distance meters, you sort of had to guess the distance before measuring. And if you didn't guess right, you guessed something else, and then you could scan for your distance. So that essentially is that you transfer your laser pulse, and then you don't look for it all the time from the moment when you transmit it until the longest distance has come back, so to speak. Instead, you just sample a small window. But in this case, we have to sample everything. So the principle is like this. Let's do it with the sound instead, because that's easy to understand. You have this guy standing here at the canyon. He hollers something. He waits for the echo to come back, and then he records everything. You're going to get a sound file looking something like this. So first, to the left, you have the direct sound coming from his mouth to the recorder. And then sometime later, you have the echo. And of course, the time difference here, if you know the speed of sound, you know the distance. We do the same thing in the instrument, so that a small portion of the light we generate with this fiber is coupled out from that fiber and directly to the receiver. That's called an internal path. All instruments that state high accuracy has that. And that is needed because all the electronics and other things have drifts with temperature and time. So, but instead of if we looking for the time difference between the transmitted signal and the received signal, that's very much more stable. The speed of sound is like 340 meters per second, and the typical sampling rate here is 44 kilohertz. That's what's used for CDs, for instance. But we're not talking about sound now, we're talking about light. And light is quite a lot faster. So it's actually 1 million times faster. So instead of these 340 meters per second, it actually propagates 7.5 turns around the Earth every second. So a sampling rate of 44 kilohertz won't do much good. So instead we use a sampler measuring 2 billion times a second. And that is fed into an FPGA for processing. And just to get a picture of how much information that is, how much data that is. So I just want to do an example. So let's assume that one measurement here, one of these 2 billion measurements, is a raindrop. I just Googled raindrop size, and it turned out that this is a complete field of science looking at the distribution of raindrop sizes, but I didn't want to dig into that. So I just picked a value like 2 millimeter diameter of a raindrop. So how much water would 2 billion raindrops be? It's not actually one barrel. It turns out that it's quite a lot more. So it's more in the order of 600 barrels of water every second. And as I said, we had this relation between 1 second pulse and 10 hours of no pulse. So same thing goes here. So the water that actually contains the data that we need to calculate the distance is actually more one bucket. So every second, our FPGA filters through these 600 barrels of water to find one bucket of water. And that's continuously ongoing, whether you're measuring or not, actually, because the EDM is running continuously. So all in all, this means that we have an EDM that can measure at 26.6 measurements, 26.6 kilo measurements per second. And now we can capture this full dome that I've been talking about in about 12 minutes. And that gives you about 10 million points. And this is something that is actually really useful and people use in field, so that you can capture a scan for every station you have. And the performance turned out incredibly good as well, actually much better than we anticipated when we started this project. So the range noise is about 1.5 millimeter standard deviation. The accuracy is about 2 millimeter, again, standard deviation. And the range is about 600 meters. So this is, for us, true useful scanning in a total station. But as I said, we also use something called interleaving when we do our band scanning. So getting the synchronization between the deflection of the EDM beam, the EDM itself, and the movement of the servo drives was really tricky. So if you want a more dense scan, instead of changing this synchronization setting and try to get the points closer together, we simply go back and measure again. So we go back, but we offset the initial conditions so that we move and place the points in between where we scanned last time. So that means that we have these fixed scanning densities. So our basic grid is 1 milliradian. Then by scanning the scene 4 times, you get 0.5 milliradians. And then by going to 16 times, you get 0.25. Yeah, you get the drill. And you can see here an example from Las Vegas where we have scanned this building with the lowest density. And then you can go in and fill points with a higher density for smaller areas that you're more interested in. And of course, they're going to align nicely. But then we also need this EDM to work in total station mode. And it turns out that since we built this EDM to capture a measurement from each single laser shot, suddenly we have 26.6 thousand real measurements every second. And that gives us all chances to do averaging and adjustment and canceling out errors. So the accuracy of this on the spec sheet is 1 millimeter plus 1.5 ppm. And in DR, 2 millimeters plus 1.5 ppm. But the good thing here is that the measurement noise is incredibly low. So in most cases, I feel that this is more accurate than our high precision instruments. Not for every measurement, but in a lot of cases it is. So it's a truly incredible EDM that can do both these jobs so well. And it gives us a true scanning total station. So then we have to produce this instrument as well.
Hey, Mikhail, can I just jump in? Got a couple of questions for you. One is, what effect does the light conditions have when scanning in the day versus night? They've heard that the scan works better in the dark. So could you just elaborate if that's true or not?
I think the effect is very small, but there is a small effect of that. So, the noise floor that we have, the light comes back from the target, and as I said, on 500 meters, it's only 1 in a billion photons that comes back. We need to detect that against the noise floor, and that noise floor is both created by the instrument itself with noise in the electronics, but it's also created by the ambient light. The good thing is that there's not that much light in this wavelength regions out there. So the sun mainly emits in the visible spectrum, and it's not at all as much energy in the 1550 range, but there is some light, and the noise floor will go up a little bit. So yes, it could probably be true that you can see some slight difference, but I don't expect it to be very big, the change.
Cool, thanks. And one other one we've got, we've said this is the instrument with the smallest spot size on the market, but regarding the spot size, you are going to potentially end up in situations, say you're measuring to the corner of a step or a stepped surface, and how does the beam determine the distance when you are measuring to the corner of something and some of the beam may be coming from another surface?
Yeah, so right now the EDM will capture the shortest distance. So if your EDM beam is split over two surfaces, so something is, so you hit half the spot hits something and the rest hits something at the longer distance, it will capture the shorter distance at this point. So that means that surface, the points will sort of overlap a little bit out in the air at that edge.
Cool, thanks. Yep, that's what we have for now. Keep the questions coming through. There's some really good ones. So, but yeah, back to you.
So looking at the production, turned out that this is by far the most advanced instrument we've ever created, and it turned out that it was as difficult to produce it as it was developing it. So we had to develop a completely new production line. It's built here in our factory in Sweden, so it's just one stair below where I'm sitting right now, which is a blessing because it means that we can have a really tight interaction between the manufacturing team and the engineering team. And we get really quick feedback when something is wrong, and we can help them out and actually be on site helping them solve problems. So each instrument, after being assembled, goes through 10 different calibration stations. Everything is logged in our database, so we have full traceability, so we know exactly which batches of components were used in which instrument, and then we can trace that back to see patterns with the production results. You can see 2 calibration stations here. The one in the middle is where we align all the different optical channels. So all these different tubes are collimators for different wavelengths and different purposes. So we use this together with the instrument to align everything. We do this on the instrument level because otherwise we would have to place the optics in some type of rotation table, and that doesn't really make sense because there's not many rotation tables that are more accurate than the instrument itself. So we use the instrument as a production tool, more or less, to do all these alignments. And on the right, you see our deflection calibration station. You can see on the monitor there you have a couple of spots along a diagonal line. That's actually the laser spots being deflected. So the purpose of this tool is to measure the exact direction that each laser shot goes out through the front lens, so that we can use that to give you accurate data. So for each rotation position of this deflection prism, we measure the exact direction out from the instrument that the laser beam goes. And again, we use the angle sensors as a reference here. So the instrument itself is part of the production tool. And then we run all the instruments to temperature. So we calibrate and test all the instruments and through full temperature range. So you can see here our final test station, where we have measurement pillars, first in room temperature, and then 2 climate chambers, one in -20 Celsius, and another one +50 Celsius. And we function test everything, we test accuracy, and we do a couple of calibrations. We have targets ranging from 1 meter up to 200 meters using mirrors, bouncing the light all over our production facility. And all in all, there are more than 500 measurements that are checked to tolerance for each instrument. And each instrument being delivered has passed every single test, otherwise they go back and get adjusted again. So it has turned out that the quality of the SX10 after delivery has been actually better than we anticipated. So, and I think that's mostly thanks to this really thorough production tests that we have implemented. So that was all from me. Any more questions?
There's just one other one that I'd like to answer, was asking about the plummet and whether we have a laser plummet option. So the plummet within the instrument is as a camera plummet with a very high resolution. It has, the size of 1 pixel is 0.3 of a mil, and we have an accuracy of 0.5 millimeters for a 1.5 instrument height. But if you are wanting a laser plummet, then we do offer a laser tri-rack that you can place under the SX10 or any of our instruments, and that gives you a laser plummet, a spot size of 1 mil at 1.5 meters. So yeah, both of those options are available. The laser plummet's part of a tri-rack, which is an additional accessory if you want. But you can see all our tri-racks and all our accessories online on our geospatial.trimble.com/accessories. Will get you there as well. And a question's come in, which will lead into my statement. We had also a presentation at Dimensions on all the camera systems, and yes, we will be having a follow-up webinar. It's yet to be scheduled, but look out for that coming up on the entire camera system, so both the plummet camera as well as all the forward-facing and the tracker itself. And I think that's all we have for today. Any questions I haven't got to, I'll get to them and reply. And also, once you close out of the webinar, it's going to ask you if you're interested in a demo. So if that's something you're really interested in, I'd encourage you to say yes to that. Otherwise, reach out to your local distributor. And if you have any questions on these instruments, either through Trimble support or you can email me, derek_shanks@trimble.com. And this webinar will be available online as a recording, so you can share to anyone. And also with time zones, we weren't able to do the afternoon session like we sometimes are, so it'll be available for those in Asia Pacific region. But yeah, thank you all for joining, and that's all we have for today.